In this online lecture, we're going to see how aromaticity can affect reactions. So our only key point here is that aromaticity can explain the reactivity of certain molecules. And let me show you an example of this. And I'm going to show you how this works by first showing you something that's non-aromatic and then showing you something that is. So for example here, let's say you have this molecule right here and you decide to react a base with it. If the base is strong enough, the base could possibly rip off this hydrogen, let's say right here, and leave behind this conjugate base. Remember, we learned before in a previous online lecture that how acidic you are depends upon how relatively stable your conjugate base is. And remember, what's making this conjugate base unstable is this lone pair of electrons here. They happen to be on a carbon, and carbons are not very electronegative, so that's kind of high energy. And also, there's no resonance. These lone pair electrons have no room to run. So we would consider this conjugate base relatively unstable, and that's why this molecule would have a pKa of greater than 40. Or, in other words, it's not very acidic. However, let's look at this molecule right here. Notice the difference. This one has 2 pi bonds in it. If you were to react this molecule with a base, then again, let's say that the base rips off this hydrogen right here, then this would be our conjugate base. Now again, notice we have the lone pair of electrons here, but if you really analyze this conjugate base, you might notice something here. Watch this. Let's make sense of these pi bonds. Notice these would be the p orbitals that would have to sideways overlap. We also learned before in a previous online lecture that the top carbon could be considered sp2 hybridized, and we can put that lone pair of electrons there in a p orbital. And in doing so, what we create is an uninterrupted pi electron cloud, and it also gives us an odd number of pair of pi electrons, which simply means that this conjugate base happens to be aromatic. This, in turn, remember, means that this conjugate base has a superstability, which means the pKa of this molecule would actually be around 15. Notice that makes it a lot more acidic than the previous molecule. And simply what's explaining his extra acidity is the fact that his conjugate base happens to be an aromatic molecule. So notice aromaticity here is explaining why one molecule might be more acidic than the other. This is one of the many reasons we want to pay attention to aromaticity. Let me show you another example here. Let's say we were to react this molecule right here. And let me remind you, we learned in a previous online lecture of a mechanism called SN1. And if you remember correctly, in the SN1 mechanism, a leaving group spontaneously falls off. And typically, halogens could act as leaving groups. So let's see if we could determine how likely this Br would spontaneously fall off like this. If this happens, we would end up with this as a result. Notice that top carbon is a carbocation. He's sp2 hybridized, therefore he has an unhybridized empty p orbital. And if we were to make sense of all the other bonds in this product here, we would see that all the pi bonds would have this p orbital arrangement. Notice what you have here is an uninterrupted pi electron cloud, and you also happen to have an odd number of pair of pi electrons. That simply means that this product right here is aromatic, which means there is a pretty good chance that that Br would spontaneously fall off. In other words, this would be a pretty good substrate in an SN1 mechanism. So that's all I'm trying to get across here. Again, aromaticity can explain the reactivity of certain molecules. That's why we'd like to be able to quickly determine if something is aromatic or not, and therefore use it to make predictions about how a molecule might behave.